batteries are becoming very big. These grid scale batteries, because they're big, they're no longer necessarily negligible price takers, which are the standard assumptions that people make that like maintains like good functioning, competitive equilibrium in markets. Rather, because these batteries are so large, their behavior, charging and discharging, shifting energy itself across hours and across settlements, they can affect the market prices. And because they can affect market prices, it is natural to ask, like, if they can move markets, then are they still aligned with the system operator? Regulators, such as in California, which arguably has the biggest batteries right now, relatively speaking, are concerned. They said in the Storage Default Energy Bid Initiative that none of these storage resources are currently subject to market power mitigation. And the CAISO, the regulator in California, believes that it is important to develop mitigation measures to manage market power, given the rapidly growing number and influence of energy storage resources. So this shows that battery market power is not just a theoretical concern. The system operators are already thinking about the effect and the mitigation. Before we think about mitigation, we have to better understand kind of like what exactly are the types of distortions and the magnitude that we are dealing with. And to do that, we first have to look at what are these batteries doing in the first place in these electricity markets. So prices in renewables heavy markets like California and Texas are determined by net demand, not by total system demand. And the net demand is the system demand minus renewables. These are the component of demand that needs to be covered by dispatchable, like conventional resources like natural gas, because these are the types of resources that have positive marginal cost. And if you look at the, this is just an example of Los Angeles, but like everywhere else in California would look the same, which is that this, you have the off-peak, which is around noon, which is low, and peak around 7 p.m. And this is in 2019. And when you look at 2020, 2021, 2022, 2023, these off-peak are getting lower and lower because the solar, which is high on at noon, is increasing year over year. So the off-peak is going down, but the peak is still staying the same because the sun has mostly set already. This is where people come back from work. And so this ramp is deepening every year due to solar. And batteries are a perfect tool for this because they can shift energy across time, say from off-peak, when energy is cheap and plentiful, to peak, when energy is scarce and expensive. But as we said before, these big batteries might not be aligned. By the way, you might already know, but this is called the duck curve because this ramp looks like the neck of a duck. The duck looks cute, but the actual ramping, not so much. We want to alleviate this. Ooh, what's going on?
Yeah, somehow you.
What's going on? You crash.
Maybe you dropped and enter, but anyways, share it again. That will be fun.
Is it?
Yeah.
Good now? Yeah. So strategic behavior of batteries is not just a theoretical concern. We have already seen in the like storage default energy bid initiative that people are thinking about it. They also published a special report on battery storage, which
Hi. You dropped off the Zoom again.
Zoom. Would it be better if I like use your computer?
Yeah,
Maybe my computer is unstable.
You just send
What?
send us. Oh, I already have
I already.
it. Great. Oh, sorry. Oh, wait a minute.
Meaning that the battery is kind of like systematically avoiding part of day-ahead scheduling and show up in real time. Like this is one of the distortions we see that we will see later can be rationalized by our model. Okay, so this paper in one slide, we have already motivating that the batteries are now big. Because they're big, they can be strategic, they can move markets. So how does strategic battery operation distort day-ahead planning and real-time balancing relative to centralized operations? In the sense of like, how do they distort and what are the effects of distortion? Can we quantify that? Our model, we are looking at a T-period to settlement market with day-ahead scheduling and real-time recourse and two types of conventional generators, slow generators and fast generators, that the mechanism we would identify that the battery is distorting their behavior in three ways: in quantity withholding, day-ahead to real-time shift, and weaker real-time response. We then quantify the effect of this distortion through the price of anarchy metric, which is an incentive misalignment welfare metric, and show that in the case of like monopoly battery, the price of anarchy is always bounded below by 9/8 and bounded above by 4/3, so that there would, on the one hand, there would always be some amount of incentive distortion, at least 12.5%. But on the other hand, like it is always bounded by 4/3, so like 33.3%, showing that even though there are distortions, they are bounded and not that large, even in the worst case. We would also show that competition, when you have like n batteries, this can significantly alleviate the incentive misalignment to the order of 1/n squared. On the other hand, if you use some power mitigation measures, if you don't know what you're doing, it can backfire. So you have to be careful. Okay, so we have gone through the high level of what we are trying to say about strategic battery. Let's now go through the model in more detail. One main feature of electricity markets that you might already know is that in the United States, at least, is that they settle in two stages. The day-ahead planning first, followed by real-time balancing, where the day-ahead market is based on forecasts, and the real-time market is based on realized demand. What is the day-ahead market for? One is that it is a forward market, so it reduces uncertainty for market participants. And even more relevant for us, we have different types of generators. Some are slow, like coal plant or nuclear plant, that take time to start and ramp up, so they can commit in day ahead, can no longer change what they do in real time, versus some others, like fast generators, like natural gas, that can ramp up and down quickly. So these two settlement allows the different types of generators to express how they behave. Versus the real-time market is here because in real time, where like power physically flows, demand must equal supply at all time to maintain stability. So
why do you say that the market is not physically binding? I mean, to be able to make all payments, you really have to turn over your dispatch to the system operator.
yeah, what I mean is just that like it's just that this one the day ahead market like clears it 1 day ahead of actual power flow, so that the power is not flowing right now, and you can change this quantity later in real time by like buying and selling. But it is financially binding in the sense that you are responsible for the power that you commit at that price. And that if you can't do that anymore, you have to like either buy or sell the energy to.
I think California is also physically binding.
Yeah, I guess it is physically it is physically binding in the sense that you have to do it. Plus, yeah, maybe it's not the not the best term. Just kind of like just that like it's like you have you
can be financially binding.
Like you can
California is physically binding.
Yeah. Yeah, like in our model, like what we need is that they have the day ahead quantities clear at day ahead prices based on like demand versus supply day ahead. The real time market clears at real time prices based on like the part of demand that can be wrapped up and down in real time, and that like, these quantities are like responsible. Okay, so this is the model in more detail, but like high level enough, is that the key player in our model is the battery, right? I mean, like in the base model, we just imagine there is like a one monopoly battery that has like sufficiently big capacity, so that and so you arguably this is the worst case where like the battery is like very powerful. Right, it is monopoly, and it is not capacity constrained. And you are deciding how much you charge or discharge in day ahead, ZTDA, chosen before the day. These are scalars. And the real-time policy, ZTRT, which is depending on the history of demand up to time t. So you're optimizing over both scalars and policies. And subject to energy balance, which is just that imagine that this is over a day, and the charge and discharge, net discharge equal net charge equals net discharge over the day for day ahead and for real time. And you have the net demand process d1 to dt, which is drawn from a joint distribution pi, which is assumed to be known. Because of this joint distribution, the demand can be stochastic as well as correlated across times. And we are looking at how the battery behaves in three regimes. The no battery regime, which is a benchmark, the centralized battery regime, where the battery is trying to minimize system costs. So this is the ideal case. And the decentralized battery, where the battery is an independent operator trying to maximize its profit. And we are comparing between these, the centralized and the decentralized. So how are prices formed in day ahead and real-time market? Basically, this is a stylization of what we already know and is standard use in locational marginal pricing in day ahead and real time. But here, we are looking, we're imagining that there are two types of generators, slow generators, which have to commit in day ahead. And in real time, it is fixed, so it can no longer adjust. Whereas fast generators, it can participate in day ahead, as well as adjust the output rebalance in real time. And the battery, we have already seen, is choosing scalars in day ahead and policies in real time, such that you have supply equals demand in both day ahead and real time. Basically, the day ahead is trying to clear the forecasted net demand, mu t minus z TDA, because you have originally the expected demand, mu t, and if you are discharging, you are reducing the amount of energy that generators need to produce, and vice versa if you are charging. So you are trying to clear this with slow and fast supply. You assume that you know the supply stack of the slow and the fast generators, so this thing would pin down the day ahead price. When it comes to real time, there is the realized real-time imbalance that has to be cleared by fast supply only. And so this pins down what the real-time price should be.
A question, when the battery doing on the real-time market, is it based on 1 2 time t or 1 2 time t minus 1? Is there some difference between them?
So here, we are assuming that at time t,
they know the current.
The dt is realized, and then you can choose you can choose the policy that can respond to that can respond to the realization of demand. And I think that in practice, probably there are some kind of intricacies around it. Maybe you kind of don't know it exactly, or whether you know this one before or after, but we abstract away from that.
I see. And you may also try the clicker. I think it works.
Yes.
Yeah, it works.
Yes. So first, what does the centralized battery do? The high-level takeaway is that the centralized battery, if it is a monopoly, and it is, well, for the centralized battery, it doesn't matter how many there are because they are all coordinated to minimize system costs. It would be maximally smoothing. The intuition is that suppose you have peak demand, and if you have off-peak demand, and if you want to minimize costs, you should shift energy from when it is expensive in peak to when it is cheap in off-peak, up until the two periods have the same marginal cost. And then this would minimize system costs. Or equivalently, you can say that here, in day ahead, you smooth all the demands to mu bar. And in real time, it is a little bit more subtle because at time t, you only know what has the demand realization up to time t, so that you kind of maximally balance the realized demand up to uncertainty in the future, which is taking expectation over that. This is kind of hand waving. You can actually write down the dynamic optimization problem, and being very careful with your algebra, you would actually get this result. which basically just says that centralized operations smooth as much as possible of the predictable components and balances shocks as information arrives. So this is the benchmark. What we are interested in ultimately is a decentralized battery, which is that how much does it deviate from the perfect smoothing that we see? And we see the three channels that the battery can exert market power. Like one is quantity withholding, where the price impact makes the battery lose less energy. Second is day-ahead to real-time shifting, where you have the sequential day-ahead then real-time clearing that can make the battery delay like some output day-ahead into real-time, leading to temporal misallocation. And the third one is weak real-time response, meaning that the battery is supposed to smooth the realization of demand in real time, but it is not doing it as much as it should. Okay, so these are a lot of words. What do they mean? Let me show you some pictures. The first one, quantity withholding. This is probably the most intuitive one, which is just a standard intuition around like when you have a monopoly, the quantity produced is less than the quantity produced in the ideal case. We have already described the intuition of like the perfect smoothing, which would kind of completely equalize the off-peak and off-peak demand. But if you do that, it would minimize system costs, but then the two time periods would have the same price. And so the battery arbitrage profit is zero. The battery would not do this, it would only partially do it, so that it would have some quantity so that it can make some profit, but would also kind of like have some price gap so that they can make profit. And you can quantify how much this is. The second one is that you are like delaying out some output from day ahead to real time. You can draw like a picture of the price demand curve, price quantity demand curve, where this is the day ahead profit, and this is the real time profit, which, okay, there are two squares. You can see that like if you want to maximize the area of two squares, if you want to maximize the profit, you actually want two separate squares like this and not like one big square, meaning that like you would actually have some component in day ahead and some component in real time. And the real time responsiveness is basically the same intuition as quantity withholding, except this one is in real time, where you have the deviations from you have the expectation and you have the deviations. Maybe the demand is higher than expected or lower than expected, and the battery is supposed to charge or discharge to compensate for this, and it is only half compensating. Yeah, so you can like write down a little bit more formally and quantify that, hey, if we say that KF is a fraction of fast generators, then you can say the quantity withholding is like ratio is like 2 minus KF divided by 4 minus KF, which means that like as KF goes up, the more fast generators there are, the less quantity withholding you have, because when you have more fast generators, like the market becomes more flexible, and so you don't need to withhold as much. Whereas for shifting from day ahead to real time, we can prove that like in centralized, you are doing all your balancing in day ahead in expectation. In real time, you would do zero. But in decentralized, you would actually do like positive amount of balancing in real time. And this quantity shows you that like the ratio to, in some appropriate sense, that the real-time share of expected discharge is KF over 2, meaning that if you have more fast generators, you actually do more shifting from day ahead to real time. And you do this intuitively because if you have more fast generators, real time is a more attractive market for you because it is more responsive to your behavior. So that you would rather do it in real time than do it in day ahead. And the third distortion is the reduced real-time responsiveness, where you can basically write down, you can write down some long algebra, but basically look at like, this is what you are doing in real time, which has the predictable shift from day ahead to real time, which we have already seen, plus the shock response, which is like how much you are like actively responding to the realization of demand in real time, which is like exactly one half. In the decentralized is exactly one half centralized, so that this channel is always 50%.
Some joint ownership between storage and fast generators, or they are independent?
So here we assume that the only strategic player is the battery. You have slow and fast generation.
He doesn't own any other form of generation.
Yeah, the slow and fast. Yeah, the battery does not control the generators, and that the slow and the fast generators are represented as like basically static, like supply stacks. I think the intuition behind this is that the ISOs often already have like a fairly good idea and like rules to like control the market power of conventional generators. Like you have like systematic audits, and you know what the fuel costs are, so that like you can be reasonably sure that these generators are bidding marginal costs. Whereas like for batteries, you don't actually know what the correct bits is.
So the batteries are trying. The objective of the market power in behavior is to try to amplify their arbitrage profits.
Yes. So in the decentralized regime, the battery is choosing the Z's, choosing the charge and discharge to maximize its own profit, taking into account that like it knows that like the charge and discharge is affecting the market clearing prices that they have to pay. Whereas like the centralized one is the ideal case where you imagine that the ISO controls the battery and uses it to like minimize system costs.
And how is that affected by virtual bidders?
Yes, so we actually have we would actually like talk about virtual bidders as kind of like one of the like market power mitigation measures later, but like spoiler alert is that virtual bidders actually can like make things worse in this model because it basically like clamps down the day ahead to real time temporal misallocation, but like by basically clamping down this channel, it kind of like amplifies the quantity withholding channel, which is like worse because now the quantity just disappears rather than delayed. All right, so we have seen basically at kind of like a medium level of like what the type of results look like in the full paper. You have kind of like closed form characterizations of these things, which you can interpret as three types of distortions. Now we know how the profit maximizing battery is behaving differently. We want to know, so what? Like, what is the effect on the system? The objective here is the system cost. Ultimately, we want to reduce the cost needed to run the system to satisfy the exogenous demand. We can show here that we have this cost ranking, meaning that the no battery is the worst. And obviously, if you are centralized, minimizing system cost, it is the best. And the decentralized battery would, that even though you have like a selfish battery, it is better than having no battery at all. So that the decentralized, which means that the price of anarchy, we can like define it like this, where the numerator is the cost reduction you can achieve in the centralized world versus the cost reduction you can achieve in the decentralized world. This price of anarchy is well defined. It is always at least 1. The closer to 1 it is, the better. How much incentive misalignment there are? We can prove that for any horizon t, And for any demand distribution pi, which remember can be correlated and stochastic, the price of anarchy is always been 9/8 and 4/3, meaning that the decentralized storage captures 75 to 89% of the decentralized cost reduction. Like just having a selfish battery already captures most of the gains you could get in the system. The proof is quite non-trivial because you have like general distributions, but we have but like one elegant thing that we can find is that remember that you have the decomposition where like where the real-time decentralized is equal to something plus like 1/2 of the centralized. Meaning that like ultimately we can only look at the centralized one where you have the decomposition such that the centralized real-time smoothing is in some sense like orthogonal in a vector space sense to the residual shock. It might not actually make too much sense here, but like you can take my words for it that like that it works and it would lead to basically the cost reduction leads to kind of like the predictable cost reduction plus the like unpredictable like variability cost reduction that you can directly compare, leading to this direct bound.
Can I ask just two clarifying questions? One is, so I want to make sure I understand precisely what you mean by centralized and decentralized. So centralized to me, it seems, what you mean by that is the market operator is managing the battery for market level objective, right?
Yes, like the market level objective here is the system cost.
Okay, and the decentralized one, actually, there's just one single merchant battery operator. So the utility is centralized into one operator, but it's not, say, the market operator who's trying to optimize the system level costs.
Yes.
Is that correct?
Yeah, so in the base model, you have like one decentralized battery, so just like one player that is trying to maximize its profit. I mean, the prices are still determined by like supply equals demand in like in an L&P sense. But because the battery can move markets, they are not necessarily optimal anymore, and we're trying to quantify like how in what ways and they are suboptimal.
Okay, last clarifying question is, in that decentralized case, is the solution that the policy that you're considering for the decentralized operator, is it causal, or maybe another way to say it is, does it assume like full information? That is, it's now a price maker instead of a taker, so it understands how its bidding, how its pricing quantity will impact the clearing price?
So here we assume that you know this, you know the system environment, so that you know the slow and the fast supply stack, so that you can calculate
where you is the decentralized operator.
Yeah, where like you, the decentralized battery can calculate your price impact. You don't know future realizations of demand though. So that like the ZT-RT like depends only on D1 to T, so that like you can choose the real-time decisions depending on the realized history up to that point. But you do know the like generators, the supply stacks.
Got it. I think
in the centralized, what do you assume? What's the market participation model? I mean, how do they participate in the market? I mean, the battery is still owned privately. So what does the system operator know?
So I mean, in the centralized thing, like you imagine as if the battery operates like as if the system operator controls the battery, so that like the system operator
knows, has plenty of information about the state of charge.
Yes, because I mean the we just assume that the battery has a. So here I think that in the base model, like the battery is big enough that the state of charge is not binding, so that like the only thing it has to be true is that net charge equals net discharge. In the extension, you assume that the battery has finite capacity. And yes, and then you can track the state of charge across time, which is known to the system operator or to the battery operator that is maximizing profit.
Because one of the prevalent mechanism for manipulation is the batteries are manipulating their state of charge information. That they don't, the system operator doesn't know what the state of charge is, and that's kind of the way to exercise market power.
Yeah, so I guess I mean like here I think that we use a relatively simple model where the system operator only cares about kind of like how much like charge and discharge power there is in each like time period and do kind of like supply demand intersection like time period by time period. I think that ERCOT is basically like this. I think in CAISO there are some kind of like complications because like you said the system operator tries to like micromanage your battery by like asking you to say, hey, how much is your state of charge? We are gonna schedule it for you, which is like which makes things even more complicated. But it's like not directly captured here. Yeah, so so far we have been looking at like the case where you have kind of like one monopoly battery that has kind of like basically infinite capacity. So it's like the worst case. Right now we're looking at N batteries. You can basically go through like solving for like centralized and decentralized battery strategies in closed form as before. These are like in Kuno competition, and you can also prove analogous bounds where the price of anarchy is at most 1 plus 1 over n plus 2, and greater than or equal to 1 plus 1 over n plus 1, n squared plus n plus 2. This one reduces to like 9, 8, and 4/3 bound for n equals to 1. So that the incentive misalignment is like 1 over n squared in the worst case, which means that competition is very effective at aligning incentive, with the caveat that with more competition, the battery profit is also reduced, which may discourage entry.
What is KF again?
So KF is the fraction of fast generators. So like you can imagine that kind of like at each price point, like there are kind of like the KF of fraction of the generators are fast, and like 1 minus KF is slow. So this is kind of like an assumption that you can make.
Okay.
I mean, you don't have to make it, but like if you make it, you would see more insights.
One question: if you want to hold this kind of theorem, I mean, just clarify. We need to follow like all the modeling and the strategy for you to trade the market, right?
Sorry,
I mean, if you want to prove the theorem here, the PLA, the bound of upper bound, lower bound, we need to follow the modeling of the market and also the strategy.
Yeah. I mean, it depends on kind of like we first derive strategies, and then we kind of like we quantify the price.
I think that the strategy here is, I think it's like heuristic strategy to.
No, these are not heuristic. Like we have like provably optimal strategy, which have the form like these, right? Like this with like these is like the real time strategy where like the real time CN is given by something that looks like this, and this is a day ahead strategy. So you can kind of like work them out. I don't show all the algebra here, but like yes, but like we proved these bounds from first principle. So we didn't kind of like reduce this as like a corollary of some like congestion game or other like kind of like price of anarchy metrics.
Two questions. Do we need any detail about the generation cost? Kind of like currently it's just a generic. Do we need any detail to understand these results or to derive these results?
But yeah, I think that like I kind of like skip over this, but like in the base model, we assume that the supply stack of like slow and fast generators are linear. Which is kind of like roughly correct for CAISO, but not for ERCOT. And we would like briefly discuss later on like what happens when you have like convex nonlinear supply curves where you get like slightly worse bounds, but still kind of like provable bounds.
I see, I see. When you say supply curve, that means the quantity versus price.
Yeah, so it's like it's kind of like at each given price, like how much generation there is below that price.
I see.
Right.
And the second follow-up question is, I think at least in real-time market, the optimization problem is kind of like stochastic optimization problem, right?
Yes,
Yeah.
I mean, you have the day ahead and the real time, which is, I guess, I mean, it is, I guess it's not quite stochastic because like, yeah, I guess I mean stochastic in the sense that you make decisions and then you have recourse.
Yeah.
But you are like basically optimizing a bunch of scalars and like a bunch of like policies or functions.
Yeah, can you just, maybe it's just to remind us or maybe give us some detail on, in this case, what's the objective really captures?
So the objective is the total system cost for centralized.
Yeah.
And battery profit for decentralized.
Yeah, but for real-time market, in which sense battery profit? Because I do not know what will happen in the future.
I mean the battery makes profit because the battery is still charging and discharging in real time.
Yeah.
And the real time battery profit is the real time quantity times real time price. You get to choose real time quantity, and the real time price is the result of of market clearing, which depends on the.
When you talk about for no competition between batteries, what's the strategy space? I mean, what's the strategy? It's a pair of charge discharge or
Yeah, so like it's like the strategy is like the ZT like these, right? So here, here in the monopoly case, the monopoly battery chooses ZTDA scalars and ZTRTs, which are policies. In the oligopoly case, each battery chooses ZTDA and ZTRT of its own, and it becomes crucial competition because all these like quantities basically additively combine to become kind of like net to go into net demand of that period. Does that make sense?
well, the way the battery operates is different than the generator. And so I'm trying to understand here, like what would be the equivalent of a demand function for a battery?
Yeah. So I guess
Demand charges of one, it's a pair, charge and discharge.
yeah. So I guess
Find the points.
yes. I think what you might be saying is that perhaps the battery is not specifying like quantities, but rather they are specifying kind of like charge discharge curves, right? Which is kind of like if it is at this price, I would charge this much. If it is at that price, I would discharge that much. I guess this is kind of like a modeling decision that we decide to let the battery kind of like operate in this way, which is kind of like equivalent to the charge discharge curve representation in the monopoly case. They're not equivalent in the Kruno case, but I guess I mean like then that they're pretty convoluted.
I'm trying to understand what would be the Kruno game for a battery, like how that works. So
Yeah, so I guess I mean like the Kruno game is like this, right? The slow plus fast supply must the price at DA must clear this one. So like rather than mu t plus ZT DA, you imagine mu t plus sum of the ZT DA for all the batteries.
but do you also impose the balance constraint, the fact that the amount they charge in one period has to discharge in the other period?
Yes, I mean each individual battery has to satisfy the balance constraints in day ahead and real time. So like each battery is kind of like choosing ZTDA and ZTRT like subject to this, subject to the energy balance condition, such that the day ahead and real time prices are determined in this way with like summation in front of the z's. Like, I mean,
how much remaining? We only have like
yeah, okay, yeah, yeah, okay, let me briefly about how like whereas competition is very effective, like market power mitigation can backfire. Like you can imagine like a few natural interventions. One is that like we have seen like the evidence of market distortions by like shifting day ahead to real time. So we can require the expected real time discharge to be zero. Or you can add virtual bidders to compress the day ahead and real time gaps. What happens is that because you are compressing the day ahead to real time shifting, they go down. But in the quantity withholding, which is another channel of distortion, would like rise, which is worse because now the energy is withheld rather than delayed, leading to lower battery profit as well as higher system costs, so that everyone is worse off. You can also imagine like subsidizing discharge in target periods if you think discharge has positive externalities, but it turns out that the subsidy cost together would like exceed the cost from the original market in the first place. So we can prove, and this is actually quite a lot of elegant theory that we're not shown here, that like our base model continues to generalize with the main picture of like price of energy bound, with operational frictions like battery inefficiency, like if you charge and discharge and then you are losing a fraction eta of the energy. If there are ramping costs for generators, where like when you increase the amount of generation, you have to pay some more ramping costs. You look at alternative balance constraints, like rather than like saying that the day ahead and real time has to separately sum up to zero, we just say that both of them together sum up to zero. Or you're looking at battery that has like finite capacity, so that you also have to track the state of charge over time, rather than just saying that charge and discharge must net to zero, as well as looking at battery investments and operations, so that you first decide how much battery capacity to invest in, as well as operate it in the centralized versus decentralized way. You can look at non-parallel linear supply curves, so that there is not a single fraction kf of fast generators, but that they change over time, but that they change for different price point. So far, we have assumed that generators are non-strategic, which I argue are like a reasonable assumption. But you can also look at strategic generators, and the results continue to hold. Capacity batteries don't have to be identical. They can have like differently sized battery, it would still hold. As well as convex inverse supply curves, this one is leading to slightly different results, which actually has a lot of interesting theory behind it. But here it is suffices to just show like results here, where rather than assuming that the price curve is linear, so like R equals 1, you can look at beta q to the R, so that it becomes an increasingly convex as R goes up. And you can see that as R goes from 1 to 5, 5 is like very convex, but still like the price of energy bound goes up, but not by much, like from 1.33 to 1.5 in the n equals 1 case, or like for n equals 2 case, like 1.12 to 1.15, which shows that like our like qualitative results continue to hold. And we can also fit this with real data from California and Texas, and we do see that the price of energy is bounded and nice, and that competition is effective. So to conclude, we have shown that strategic batteries distort storage values along 3 dimensions: quantity withholding, delaying from day ahead to real time, and under responding in real time. The welfare loss as captured by the price of energy is real but bounded and disciplined by competition, and that our results continue to hold in general settings. So I don't know if you want me to, this is the end of the paper. I can continue to talk about other works briefly, or you want me to end here? Both work for me.
Yeah, why don't we end here?
Okay,
Yeah, maybe we can open floor for them to ask.
Sure. You can also do that, photo and then questions. It's pretty easy. Questions during photo. Just very good at that.
Hey, how about? Oh, maybe let me do that. You know how to do that? The red button. Yeah, copy.
all right.
Just to take a photo together.
Yeah, all right.
Wanna go to the
First
To the
page?
first page, yeah.
And do you want Professor Oren to join us? Take a photo together.
Professor Oren is always ready to be a photo.
All right, here it is. Yeah. Where should I? Oh, I guess we know the students here or just the.
You gotta make sure you can see the slide.
Yeah.
Oh. Wait, where should I? All right, I guess.
Maybe you sit close to them, like.
It's just there here.
Yes, also perfect. Okay, wait, yep. 3, 2, 1.
Fine. And do one more.
Oh, there's a Polaroid.
Yeah.
Should I take it first and?
Was it last one?
Close up.
Who wants to do it? I mean. All right.
If I come close, I can, it's helpful to get all of you guys in the camera, so maybe you need to move to that. Yeah. Okay, it's good. 3, 2.
Thank you.
Okay.
Thank you so much.
Now we can take questions.
No.
I think we had a lot of questions during the talk already.
Yeah.
Oh, we have one behind.
Yeah, you mentioned these like other operational functions like inefficiency and changing the constraints so that both markets together sum to 0. Did you find like the same takeaways under all of inclusion of those operational functions, or were those sort of not included in the study here?
What do you mean, like you see the types of distortions? Yeah,
Yeah,
you see the same types of distortions. So like basically kind of like all the insights continue to hold, which is why kind of like we show this and then like we show the extensions later. I mean, I think we do need to develop like new like mathematical tools to deal with these, but like in terms of like managerial and like economic insights, that they are the same.
I got some questions.
Uh-huh.
So first from the start, you mentioned that duck distribution rate, and you observed that each year the distribution is a bit different.
Uh-huh.
So that's also what we see in our cow market, and that's kind of like a yearly distribution shift.
Uh-huh.
So in your modeling, do you, like have,
Yeah, we don't actually model distribution shift here, like we do, yeah, like in the model, like you kind of like assume that like the demand like D1 to DT is like drawn from a distribution pi, which is known to everyone. So that, yeah, I mean, like we don't really capture this. I think if the goal is kind of like get kind of like a policy that works, like that is like deployable, we definitely have to do that. But I guess I mean like in this work, like it is more kind of like an analytical modeling to identify kind of like different like qualitative behavior, like so we don't do that.
okay, I see.
Yeah.
And another question is, I see that in your 3 observations, something like that, there's quantitative withholding. But I believe most batteries or battery storage systems in the industry, they are still purely seeing themselves as price taker.
Uh-huh.
They are not considering like the price changes with their behavior. Do you think if you change your modeling to they all seeing themselves as price takers, will the conclusions change with them?
Yeah, I mean, I think that like we are doing all of these, we are doing all of these because like the batteries are not price takers, right? I mean, like if people see themselves as price takers, or if they are small enough that the price taking assumption is adequate, then like everything would go through. We would basically have kind of like competitive equilibrium with like optimal social welfare, just like in the just like in the generator case. And I think that was known before, that like price taking batteries like lead to like Walrasian equilibrium.
Yeah, I know,
Yeah,
I mean, maybe they are not price takers, but they are seeing themselves as
Yeah.
price takers as they bid. So
Uh-huh.
maybe their behavior is like based on their price taker model, but they're
Mhm.
actually not price takers. I think that might be the real case.
Yeah, I guess it is kind of like tricky to think about like um what we mean by that. I think that like one thing that is probably relevant and is like not done here is that here like you assume that like everything is clearing in the same market or like there's like a one bus which is kind of like probably kind of like a good like first order approximation for like markets that are either like not very congested and so they're all connected, or that they are kind of like very congested outside so that they're isolated. And I mean, I do think that like batteries right now can have an effect on prices even if they're not very big if they are in like specific locations that are critical. And this is like not something that we do here, but it is something that I want to look at. I guess regarding kind of like how you bid when like you think of yourself as price takers, even though you aren't. I guess it is a little bit tricky to think about. I guess I can get back to you later.
Thank you.
Any other question from the audience, or maybe you check if there's any question from the
There is
Zoom?
indeed. Questions?
There's no question.
Wait, how do I?
Okay. I don't think there's any.
No, there's
Yeah, only three people.
only people are left. Okay.
Okay, yeah, maybe. I should stop sharing.
Okay.
Okay, maybe we will end up here and feel free to chat with Jerry afterwards.
Yeah.
Next week we will have another immerse seminar talking about electric vehicle charging and it's relevant to other kind of like local businesses. So welcome to join us next week. Thank you for coming today.
Yeah, and thank you for inviting me.
Yeah.